there is a telescope forcing the world's smartest people to rethink a single question: where did the universe actually come from? It's not because it captured something weird, but quite the opposite. What it captured was too normal. So normal that, according to our current physics, those things shouldn't even exist. This telescope is the James Webb. Humanity spent nearly 30 years and over $10 billion to build this ultimate eye in space. After starting its job, its first major act wasn't helping scientists verify theories, but rather taking those theories and poking holes in them one by one. And the holes are getting deeper and larger. Let's talk about the first hole. Webb pointed its lens at Ursa Major and received a batch of light that traveled over 13 billion years to arrive. Imagine this concept: from departure to being captured by us, the time these photons traveled is millions of times longer than human history. They crossed countless galaxies, countless gravitational fields, and countless celestial bodies that we haven't even had time to name, finally landing on Webb's detector. This light comes from a group of galaxies born after the Big Bang, just 500 million years later. 500 million years sounds long, but you should know our universe is 13.8 billion years old. 500 million years is its infancy. At that time, the entire universe was like a newborn baby, unable to even crawl, let alone walk. At most, it was a busy cloud of hydrogen and helium gas drifting around. But these galaxies had already grown into behemoths similar in mass to the Milky Way. Stop and think about that carefully. A galaxy the size of the Milky Way contains 200 to 400 billion stars and is nearly 100,000 light-years wide. According to our cosmological models, forming a galaxy of this scale requires billions of years of accumulation. It needs gravity to pull and compress diffuse gas and dust bit by bit. Ignition is an extremely slow and precise process. But these guys, in only 500 million years, had already reached this mass. It's like planting a seed in the morning and going back in the afternoon to find a massive ancient tree that takes 10 people to hug. It's not a surprise, it's a crisis of logic. You start to wonder if your fundamental understanding of time is flawed. Scientists nicknamed these galaxies the universe breakers. The name is quite direct, because their existence almost completely shatters our theoretical system of galaxy formation. It's not just a small leak here or a minor repair needed there, it's a subversion that shakes the very foundation. But this is just the appetizer. Webb then reopened another old wound that had troubled astronomers for decades. This wound has a specific name: the Hubble Tension. It sounds very academic, but simply put, it's a collective headache for scientists. We use two different methods to measure the expansion rate of the universe, and the results just don't match. Scientists use the Hubble constant to measure it. According to the standard model, theoretical calculations suggest this value should be about 67 kilometers per second per megaparsec. But whenever real cosmic observation data is used for calculation, supernova explosions, red giant gravitational lensing, Cepheid variables, every possible method has been used. The results consistently fall around 73, off by nearly 10%. 10% doesn't sound like much in daily life. Like a 10% discount. No big deal. But in cosmology, this is an earth-shaking level of error. Think of it like this. Like using two rulers to measure the same table. One shows 1 meter. The other shows 1.1 meters. And both of these rulers were built by you using the most precise instruments and the most rigorous physical principles. You can't say either one is a defective product. In this situation, there is only one possible problem. Some of our fundamental understandings of the universe were wrong from the very start. Scientists waited decades, thinking as observation technology became more precise, this crack in the numbers would close automatically. Thinking it was measurement error. Thinking the data wasn't refined enough. Then Webb arrived, with the clearest observations in human history. The deepest and most accurate data ever sent to space. The final conclusion was, not only did this crack not narrow, it actually stretched even wider. This is quite unsettling. Consequently, a group of scientists began to seriously discuss a direction they hardly dared mention before. Perhaps our universe is not alone. What if our universe is having some kind of interaction with other universes? Someone built a mathematical model to simulate this multiverse interaction scenario, and found the expansion calculated in this framework rate is closer to actual observations than the standard model. Meaning, what we thought was cosmic expansion might not be expansion at all, but rather stretching and merging between universes. What we thought was the entire universe might just be a large, beyond any imagination, in the multiverse, a tiny, insignificant corner. It's like an ant crawling on a piece of paper, thinking its world is just that paper. Then someone folds the paper. The ant finds the two ends suddenly close together. It doesn't understand what happened, because it has no capacity to perceive dimensions beyond the paper. We might be that ant. And at this moment, a Nobel Laureate stepped in. Roger Penrose, British physicist, 2020 Nobel Prize winner in physics. One of the founders of black hole theory. Not someone who seeks the spotlight. His research career is as rigorous as a precision instrument. His contributions to math and physics, many are at a depth where you'd need 20 years of study to understand. But this idea he proposed, coming from anyone else, would sound like lines from a sci-fi novel. The universe is cyclic. His theory is called conformal cyclic cosmology. The core idea is that our universe is neither the first, nor will it be the last. In his framework, the universe has its own life cycle. Like a living thing, it has birth and growth, aging and death. Then death itself becomes the opportunity for new life. Specifically, it goes like this. The universe was born from the Big Bang, then expanded continuously, expanding, until one day, all the stars burn out, all the black holes evaporate, all matter completely decays, decomposing into pure energy, becoming a place with no mass and no time scale, a photon ocean with no sense of spatial scale. Massless things cannot perceive time. This is a corollary of relativity. So, in this extreme state, the universe enters a peculiar, eternal state with no beginning and no end. And it is precisely in this state that some mechanism triggers the birth of a brand new universe. Like passing the baton in a relay race. The end of the previous universe is the starting point of the next. Penrose calls each of these journeys an Aeon. In his eyes, it wasn't creation. It was a handoff. What we call the universe's starting point is actually the legacy of the previous universe passed to us at that moment. This theory sounds both grand and mysterious. But Penrose did something that made the entire scientific community unable to easily say no. He said, I found evidence. Not a theoretical speculation. Not just mathematical consistency. But something that can be actually observed. Real traces written in the data in black and white. These traces are hidden in the cosmic microwave background. What is cosmic microwave background radiation? Simply put, it's the ancient afterglow remaining from about 380,000 years after the Big Bang. At that time, the universe had just cooled from a hot plasma to a temperature low enough for photons to fly freely. Thus, light was able to propagate freely for the first time. These light rays reaching us today have been stretched by cosmic expansion into faint microwave radiation, uniformly permeating the entire universe. No matter where you point your antenna, you can receive it. It is the oldest light humans can currently see. The film negative left from the universe's infancy. Penrose and his team, in this film negative, discovered something strange. Some circular patterns, hot spots with temperatures slightly higher than the background, like stamps quietly pressed onto the sky. And in the data from the Planck and WMAP satellites, two completely independent data sets, they appeared repeatedly. These circles shouldn't be there. According to the standard cosmological model, the CMB temperature fluctuations should be highly random, like randomly distributed ripples on the sea. Such regular circular structures shouldn't appear. But they are right there, one after another. Penrose named them Hawking points. The name itself is a tribute and a declaration. His explanation is this. At the end of every cosmic Aeon, supermassive black holes will slowly evaporate through Hawking radiation, releasing their stored massive energy, bit by bit. This process is extremely long. A solar mass black hole would take an amount of time to evaporate that far exceeds the current age of our universe. And for a supermassive black hole, the time required is even more astronomical. But on the scale of the cosmic Aeon, described by Penrose, there is enough time. The energy released during this evaporation will not simply disappear. They are carried into the next universe, eventually in the form of luminous disks, imprinted on the new universe's microwave background. Radiation, in other words. When we look up at the sky today, those mysterious circles we see might be black holes from the previous universe, before their total extinction, leaving one last letter for our universe. A suicide note carved in the sky. spanning an entire cosmic eon. Penrose estimated, the apparent size of these disks on the celestial sphere is roughly the same as a full moon, and what they found in the data was exactly that size. Of course, there is opposition in the scientific community, and they weren't exactly quiet either. Many scientists believe these circular patterns are just statistical noise. It's that deep-seated habit of the human brain, the tendency to find patterns in random data, acting up once again. After all, if you scatter beans on the ground, you can find all sorts of shapes. This doesn't prove the beans are sending a message, it only proves the human brain loves finding patterns. This criticism is reasonable and it is a serious one. Regarding this, Penrose hasn't given a rebuttal that satisfies everyone. His data convinced some, but not everyone. Yet Penrose remained unmoved. He said when black holes were first proposed, the scientific community treated them as mathematical freaks. A pathological solution in Einstein's equations. No one believed they actually existed in the universe. Physicists spent decades proving over and over that black holes couldn't exist in reality. And then, black holes became common celestial bodies, found everywhere. We've even taken photos of them. That orange donut photo went viral globally. By the time children are in primary school, they already start learning about black holes. Perhaps Hawking points are just the next black holes waiting to be recognized. Science has never been a matter where courage alone is enough. But it certainly requires courage to dare to propose those absurd-sounding ideas, and then use time and data to provide answers. Moving on from Penrose, let's turn the lens back to Webb, because it made another specific discovery that left scientists even more silent. Webb found a galaxy numbered JWST-Z11. Just 330 million years after the Big Bang, it was already shining in the universe. Note, this is much earlier than the cosmic breakers mentioned before. It is one of the earliest galaxies we have ever observed. That in itself is enough to raise eyebrows, but the real reason it left scientists collectively silent wasn't its existence, but what it was doing. This galaxy is releasing a massive amount of Lyman alpha radiation. This is a characteristic light emitted by excited hydrogen atoms. Fixed wavelength, clear signal. It's an extremely important beacon for astronomers studying the early universe. It is also a vital indicator of the universe's ionization process. Because only when the surrounding universe is fully ionized and the hydrogen fog is cleared away, can this radiation travel through vast space to be received by us. And that is exactly the problem. At that time, the universe hadn't been ionized at all. Let me explain what this means. In the very early stages of the universe, roughly several 100 million years after the Big Bang, all of cosmic space was filled with dense neutral hydrogen gas. This hydrogen was like an omnipresent, sun-blocking thick quilt. For any UV rays or specific radiation bands trying to pass through it, it was basically impossible. They'd be absorbed before traveling far. Clean and simple. No room for negotiation. The universe of that era was, in a very real sense, a total and utter darkness. According to standard theory, the universe waited until 300 million years after the Big Bang for the first stars and galaxies to light up, slowly ionizing the surrounding hydrogen gas bit by bit. Like lighting the first match in a room full of fog. The fog begins to clear away from around the source bit by bit. This process is called the epoch of ionization. It was long and slow. Before then, the universe was basically opaque. JWST-Z11 is only 330 million years old. According to theory, the surrounding cosmic mist should still be too thick to let light through. Yet, the Lyman alpha radiation from this galaxy just pierced through like that, traversing over 13 billion years of time and space, landing clearly in Webb's detectors. The Cambridge astronomer leading this study, Joris Wittstoke, made no secret of his shock. He said, even considering the extreme youth of the universe then, the strength of this Lyman alpha signal totally exceeded everyone's expectations. His collaborator, astronomer involved in the study, Kevin Heinlein, put it more directly, we shouldn't have found such a galaxy at all, but there it is, with clear data, leaving no room for ambiguity. Even crazier are the subsequent results. Scientists discovered this galaxy has already, around itself, carved out a diameter of an ionized bubble 650,000 light-years long. The surrounding neutral, hydrogen gas, has been blasted clean by its radiation. 650,000 light-years. Do you know what that concept means? The diameter of our whole Milky Way is roughly 100,000 light-years. The diameter of this bubble is over 6 times that of the Milky Way. In just over 300 million years, this galaxy carved out a region 6 Milky Ways wide, creating a transparent zone. According to current theoretical models, forming such a bubble requires much longer than 300 million years. What does this mean? There are only two possibilities. Either ionization began earlier than we thought, long before theoretical predictions, driven by certain early celestial bodies that started the process, which we simply hadn't discovered yet. Or the speed of ionization is much faster than we predicted. Certain mechanisms, with efficiency far beyond models, are clearing the cosmic hydrogen mist. Whatever the answer, it doesn't align with the model of cosmic evolution we have. This galaxy, what generates such violent radiation? Is it a cluster of extremely hot, supermassive young stars, dozens of times hotter than the Sun? Or is there, at the center, an active black hole madly devouring matter? During this devouring process, it releases staggering energy. Scientists are still researching this, there's no conclusion yet. But what is certain is this galaxy did something we thought was impossible for that era. And the universe never intended to stop doing what it wants just because our theories forbid it. You see, this is what Webb has been doing all along. With every batch of data it sends back, it helps the universe hand us a challenge. One anomalous galaxy after another, one mismatched data point after another. The cosmological system we were once so proud of is being pried apart, brick, by reality. And this dismantling is far from over. Some scientists say the greatest significance of these findings isn't that a specific number was overturned, or a specific theory needs revision, but that they remind us of something fundamental: scientific knowledge is always temporary. Our current theories are only right until a counterexample is found. Once nature shows a phenomenon that its theory cannot explain, then theory must give way. It must be updated. It must examine where it went wrong from the start. This is not a weakness of science. This is precisely science's most hardcore strength: its ability to overturn itself. Now, scientists are starting to admit more frankly that our understanding of this universe is far shallower than we once thought. Those conclusions once considered set in stone, those once written in the first chapters of textbooks, the vision seen as the cornerstone of cosmology, are being re-evaluated, are being re-examined. This isn't a cause for frustration. On the contrary, in the history of human knowledge, this is one of the most exhilarating moments. Because we are standing on a true cognitive boundary. Ahead lies what we do not yet know, and we, for the first time, have an eye powerful enough to begin peering into that darkness. Perhaps the Big Bang wasn't an absolute starting point, but just one leg of an infinite relay race. Perhaps our universe is just one of the countless that once existed, are existing, and will exist in the future, just one scene currently being played out. Perhaps the mysterious circles Penrose saw in the sky were truly black holes from a previous universe. When they were reaching their end, they used their final breath to leave a mark, quietly etching it into our universe, within the most ancient light. If all this is true, then every time we look up at the stars, in fact, we are looking at the final words of the last universe. That light, that ancient afterglow, those circular hot spots, are proof that another universe once existed. It's the final trace left behind after its entire life was burned away. And we, holding a telescope called Webb, are looking up at this starlit sky, trying to decipher that letter, trying to hear voices from the other side, from another era, perhaps from another warrior. We just haven't finished reading it, or perhaps we never will. If the universe truly is cyclical, if the Big Bang is just a passing of the baton, then before our universe was born, in that previous universe, was someone else looking up at their stars, also asking the same questions?